All right, hi everyone, and welcome to our last NL seminar of the semester, and my last seminar as coordinator. It's been really fun doing these, getting to meet all of our speakers, so thank you all so much for attending both today and throughout the year. And I'm very excited. Our last speaker is Jen-Tse Huang, who actually was visiting USC last semester, but we missed him while he was in town, so we're very excited to have him virtually. He'll be presenting his talk on LLMs do not have human-like working memory. So I'm very excited for this talk. He is a postdoctoral researcher at the Center for Language and Speech Processing at Johns Hopkins University, working with Mark Jen-Tse. He received his PhD in computer science and engineering from the Chinese University of Hong Kong and his BSc from Peking University. His research explores the evaluation of large language models, both as individual agents and as collectives in multi-agent systems, through the lens of social science. His work has been published in top-tier AI venues, including an oral presentation at iClear 2024. He actively serves as a reviewer for major conferences and journals such as ICML, NeurIPS, iClear, ACL, CVPR, TMLR, and Nature Human Behavior, and has been recognized as an outstanding reviewer at NeurIPS 2024 and EMNLP 2024. So please welcome Jen-Tse Huang and give it up for him.
Welcome! Yay!
Thank you so much. Thanks, Katie, for inviting me for and when Katie invited me last year, I planned to share some words from when I was visiting USC last year. But recently, I find that it will be more effective to share some recent progress. So this is the topic of this presentation. LLMs do not have human-like working memories. So let's first do a thought experiment. I invite all of you to think of an integer from 1 to 10, but do not say it to anyone. And now answer this question. Is the number greater than 5? So let me see your hands, please. Or hands, if you can raise your hands if your number is greater than 5. Oh, appreciated. Yes, so when you raise your hands, I know the number have entered your mind, since you need this number to compare this and answer my question. So the image of the number that have entered your mind is in your working memory. This working memory temporarily holds your mind and helps you manipulate information, temporarily store information, and help you calculation. In contrast, is different from our long-term memories. For example, like our name, our background, that you will remember for a long time. Working memory will, you will forget your information in the working memory soon. For example, you will forget the number you picked just a few days later. And working memory is essential for a human in many complicated tasks, like in human decision-making, reasoning, and other daily tasks. So in today's talk, the core claim is current LLMs do not have this human-like working memories. To verify this claim, I will show 3 experiments. The first one is number guessing game. In this game, LLMs produce unrealistic responses, that is, unrealistic distributions from real humans. The second one is yes or no game. In this game, current LLMs exhibit self-contradiction. And the final one is a math magic. In this game, LLMs show limitation in tasks that require mental manipulation on numbers. So let's get started in the first game, number guessing. This is a conversation between me and ChatGPT 4.0, where I ask ChatGPT to secretly pick a number between 1 and 10, but don't say to me. And it can respond plausible to me that it already has a number in his mind. And I asked, is the number you are thinking of 4? Answer yes or no. And ChatGPT just says no. So how can we verify ChatGPT's claim? We can imagine that if we ask the same question to humans thousands of times, each of the number between 1 and 10, eventually we can have the estimated probability for each number. And as long as the human already pick a number in their mind and they answer honestly, then the probability for all 10 numbers should sum to 1. The thing is, human can have their preference. Like if I like the number 5, I will answer all yes to the question inquiry 5 and answer all no's to other numbers other than 5. And the things can also be the human has no preference on numbers, so the probability of each number will just be 0.1. So I would just pause here to see if there is any question about this claim, because this is the core property in the first game. All good? Okay. If there is sorry. Is someone talking in the room? Hello?
I think they're trying to figure out how to unmute.
Yeah.
Okay, so Ulf was saying that humans won't necessarily have a even distribution when asked to pick a number.
At all, yeah.
And I was also going to ask a related question, which is, why is it desirable for LLMs to pick numbers in like a sort of human-like way? Like, this seems like a very I don't know, it doesn't seem like a super useful task.
I think because this is a essential ability for humans, but the core claim here is LLM lack this human-like ability, and lacking this ability, they will show some disadvantages on several downstream tests. The first one will be they cannot produce realistic distribution, which will show in this experiment.
Okay, cool, thank you.
Okay, so let's just keep going on. And in this experiment, we asked each of the number from 1 to 300 times, and we count the probability of model answering yes to each question. So here's the results. We picked several model families, including OpenAI GPT-1's Llama 3.3, 3.1 with different sizes, and also long reasoning models, O1-like models, and also Huang and DeepSeek models. The first conclusion is models never produce yes for nearly all the queries. That is, nearly 100% of time they are answering no to questions like, is the number you are thinking of 10, 5, 2, or 3? So they are not producing realistic distributions. And some models actually did a good job. They can produce some yes responses. For those yes responses, we can see that they have a preference over 7. So this is also observed in our human society, that when you ask human to randomly pick a number from 1 to 10, humans also have a preference on 7. This is called the blue 7 phenomenon. And how do we quantify this ability. So a simple way is to sum up all the probabilities from 1 to 10, and this table shows the result. We can see that most models have bad distribution that is close to 0, which are marked in red in this table. And we can also see that 3 models perform good distribution. The GPT-4o 0806 version and the Llama 3.18 billion version and the 405 billion version. And the next conclusion is newer models do not necessarily perform better. For example, here we can see that the newer version of GPT-4o, the November one, actually perform worse than the August one. And also OpenAI's newest GPT 4.1 version produced the sum of probability of 0. And the same is also true for Llama models, where we can see for Llama 3.3 model, the sum of probabilities is also very close to 0. And Llama 3.1 actually outperforms Llama 3.3. And we can also see that if we are using long reasoning models like O1, O3, O4, or QW2 and DeepSeek R1, they do not necessarily perform better than non-reasoning models. For example, we can see for O series model, the sum of probabilities are also very close to 0, and it's the same for QW2. And DeepSeek R1 can have a sum of 0.64, but still a large gap from 1. So in conclusion, we can see that Llama 3.1 is great. The 8 billion version and the 400 billion version can produce distribution, the sum of probability very close to 1. And the previous experiment are all about range from 1 to 10. How about other ranges? So here we are curious about the behavior of GPT-4o, the August one, and we pick the ranges from like 1 to 2 to 1 to 40, and we can see that for larger ranges, the probability sum is also very close to 0, like for 20, 30, and 40. And also, the preference of 7 still exists. And if we encounter numbers containing 7, like 7, 17, 37, they can have a higher probability of answering yes in models' responses. So the conclusion for the first experiment is LMs cannot predict.
Jay, we had a question from in the room.
Okay.
Just wondering, so are these all like closed models? I'm wondering if, this preference towards saying no is maybe something to do with like guardrails on, or like some side effect of guardrails or like hidden prompting in the LLMs. Like if we're just using closed models, I'm wondering if there's a way to remove that as a confounding factor, or if you thought about that.
Sorry, is your question about whether COT prompting or other reasoning strategies can
Not exactly. Like if you ask like a closed model like GPT-4o, certain questions, there's guardrails, or like there's hidden prompts, to make sure that it doesn't answer certain ways. And so I'm wondering, if that might be influencing why, for any yes or no questions, there's a preference for saying no. Maybe it's not specific to the problem of guessing a number.
Oh, yeah, I got your point. So your point is LMs are just like to say no instead of there are actually some numbers in their mind.
maybe because these are closed models, you can't quite tell, but I'm wondering if you tried open models, and you know what's going in, all the prompts are shown, whether this trend is kind of holding, I guess.
Yeah, I think the core hypothesis here is that if we ask the same question to humans, if humans really pick a number in their mind and they question honestly, that is, they are not answering randomly to your question, then we can always observe the sum of probabilities that is one. So if the models produce the same distribution, I mean, the sum of probability is far from one, then something might be wrong for these two hypotheses. Either the model does not pick a number, or they are just lying.
So I had a question too, like what do we mean by lying or like answering honestly here? And like how do we verify that the humans are answering honestly?
By saying humans are lying, I mean that if I am picking a number of 3 and ask me whether the number I'm thinking of 3 is 3. So here I can lie to you that no, the number I picked is not 3. So in this case, cannot observe a sum of probability of 1. That's because the human is lying.
Okay, thank you. That clarifies.
Okay. So let's enter the second part of our experiment, the yes or no game. So a thought experiment again. So here I invite all of you to think of an object, but don't say to any other person. And you need to answer several questions. First, is the object longer than a pencil? And you can remember your own answer. The next one is the object heavier than a coin? And the final one is the object smaller than a dice? And you have now you will have 3 answers in your mind. And I invite you to think about your thought process. What you do is every time you answer a new question, you compare the question object with the object in your mind and easily give your answer. In contrast, what you didn't do is look at all your previous answers to make sure that your newest answer does not conflict with them. So I will pause here again to see if there is any other question, because this is the second core property in my experiments. So I'm saying that we human will not remember all our previous answers, and when we encounter new questions, we see how to not conflict with all the previous answers. Instead, we just compare the object in our mind with the new question object. So understanding this property, we can have some similar conversation with ChatGPT 4o. And this is the conversation between GPT and me. We can see that it still gives some responses like yes or no. But how can we know that whether ChatGPT is lying, or say whether there is actually no objects in ChatGPT's mind? If we continue to ask the questions, ChatGPT will eventually show self-contradiction because it gets harder for LLMs to check the context and ensure that there is no self-contradiction, which is limited to LLM's long context ability. So here, for our experiment, we predefine a list containing distinct 60 objects and in order of 5 different physical properties. We have here volume, length, weight, density, and hardness. And in each list, we have different objects ranked from the smallest to the biggest. So for each test, LLMs are instructed to think of an object in their mind. And then we randomly choose a property and randomly pick an object from the object list and ask the LLM, is the object in your mind like bigger than a dice or smaller than an elephant? And we can keep asking such questions. And here I set 250 as a maximum number of questions. If there is no self-contradiction detected for all the questions, then this is marked as a pass. And each model is tested 200 times. This table shows the results. We can see that for a weaker model, GPT-4o mini, for all 200 tests, it eventually shows self-contradiction. And for a stronger model, that is GPT-4o, as its ability grows, the number of passes increase. GPT-4o, we can see it passes 27 tests out of the total 200 tests. So here, LLMs perform this task using their long context ability instead of comparing the object in their mind with the question object. So it should not be the case if LLMs really have a working memory to perform this task. And here, I record the histograms of how many questions can LLMs complete before they show self-contradiction. So here we can see the peak of the cases for GPT-4o centralized among 20 to 50. For GPT-4o mini, the peak centralized from 10 to 40. And we can also see that GPT-4o can have more passes than GPT-4o mini. So the conclusion for the second one, the yes or no game, is LLMs will eventually show self-contradiction because they do not compare the question object with the object in their mind. Instead, they look for cues in all of LLM's contexts. That is, every time LLMs see a new question, it will check all the answers before to see how to answer the new questions without self-contradiction. Is there any questions about the second experiment?
Yeah, go ahead.
Have you tried like longer prompts, like a chain of thought or something on like previous questions? No matter guessing a number or just having an object in so-called thoughts in LLMs, because I believe LLMs like follow instructions, but they may need like more fine-grained instructions for like to think human-like. Maybe say, guess a object and just simply ask what the object is, maybe the following questions can be more what do you call
Consistent?
consistent. Yeah. Have you tried that? Is that tested?
Yeah, actually, I tried OpenAI's O1 Mini and DeepSeek R1 before. These models are long reasoning models, and they will do lots of COT before its final answer. And we can see that it still look for cues in all over the context. So what this long reasoning models do is they check all the answers. I mean, they will analyze on all its previous answers to see how to answer the current question to avoid self-contradiction. So my point is, if we are using COT or long reasoning model, the performance can be increased. That is, we can see more passes in this figure. However, the increase is not from like this kind of model has a better working memory. It's because this kind of model has a stronger reasoning ability. It can perform reasoning from a longer context. Is that answer the question?
I had a question about, so I guess, why is the expectation that the model will have an object in mind? Because I mean, how models are trained is to, predict the next token based on the previous sequence. So, are you leading towards like some like different way of training or like some model differences? Because I just think that, this is probably expected, right? Like this result is what you'd expect based on how these language models are trained. I'm wondering if you're trying to tease out like a way to improve that. Like there's no explicit objective for a model to keep an object in mind. That's sort of a human-like thing to do, but I don't think models are trained to do that. So I just feel like the result is expected. I'm wondering if maybe
Yes.
you're leading towards it, but yeah.
Thank you for this question. Actually, this is a very good question about why we are seeking working memory on LLMs. And in my opinion, LLMs should be more human-like in the future. And currently, we can see that LLMs are not, because they lack several essential abilities from humans. For example, the working memory. And lacking this working memory may have several outcomes. For example, here in this kind of task, LLMs will eventually show self-contradiction, which is seldom shown in humans, because humans can easily answer these questions and show no self-contradiction. So I think this is a potential way to improve LLM reasoning in such tasks, other than some advanced reasoning skills like COT, long reasoning models. I think this can be easily solved if we have a specially designed working memory module on LLMs. And the second question is why we are expecting those working memory in current LLMs. So here I think this is a limitation for all the current transformer-based LLM architecture, because actually there is no such external or say extra module for these LLMs to store this information. I mean, the working memory like module. So I think in the future, if we are designing LLMs more human-like, for example, we are adding a working memory to LLMs, a possible solution will be like some special module of internal thinking added to LLMs so that they can solve this task better.
I also wanted to ask, like, so I think that this work is really interesting because there are a lot of people that are operating under the assumptions that LLMs do have a very human-like and like deep way of thinking, whereas like I think a lot of us here are more operating under the assumption that they are just really good next token prediction machines that can convincingly fake it. And so, like, what would you consider sufficient to show that LLMs have working memory? Would like passing the three tests in your talk, would you, I know it's necessary to show working memory, would you say that it's also sufficient to show that LLMs possess working memory?
Sorry, I'm not sure I understand your question.
So let's say an LLM passed all of the tests that you're proposing in your talk.
Yeah.
Would that be enough evidence to say that the LLM has working memory in the same way a human does? Or do you think there would still need to be more tests to show that working memory capabilities are comparable to a human?
So your question is whether the tasks designed in this presentation is sufficient to show LLMs have human-like working memories.
Yes.
So here in the later slides, I will mention some existing efforts on evaluating LLMs working memory, and I will explain why I think those methods are not valid in LLMs. So here, the three experiments designed in this presentation, I think we can prove that if LLMs are not doing a good job in this tasks, that's because they have no human-like working memories. But whether passing all of the tasks can show that LLMs have human-like working memories, I think we need more theories from cognitive science. But
thank you so much.
Yeah, at least we can say that if LLMs cannot pass this test, they have no human-like working memories, but not the reverse. Okay, let's enter the final part in today's presentation. It is a math magic. So I will invite all of you to play a game with me. First, please think of a 3-digit number. And the 100th digit and the 1st digit must be different. For example, we can have ABC or ACC if you like. The second step is reverse the digits of the number. That is, if you have ABC, then you will have CPA in this step. And then subtract the smaller number from the larger one. After that, reverse the result again. If your result is a two-digit number, include a 0 before. For example, if you have a result of 67, you will first prepend a 0 before, that is 067. After the reverse, you will have 760. Finally, please add the two numbers together. And here I can predict
Which
that,
two numbers?
yeah, the answer will always be 1089, no matter what numbers you pick at the beginning. So this kind of magic is also called math magic, or say math mentalism. Here, magicians can predict the results from math. So how to know that whether LLMs have the working memory required to perform such mental manipulation on the numbers. That is, if they do not have this required working memory, they will eventually show wrong results at the end. So in this experiment, we choose a more complicated math magic that is based on the Josephus problem. That's because the 1089 problem is too famous, and it's probably included in LLM's training data. And in our preliminary results, we always find that LLMs can easily identify the game, the 1089 game, and predict the final outcome. So we are choosing a more complicated one. So LLMs will be instructed to select 4 numbers at the beginning. Then we will add lots of operations, including duplication, rotation, removal, and insertion. And based on the math, that is the Josephus problem, there will only be 2 numbers left at the end, and these 2 numbers should be the same. So we can test LLMs with a randomization of the operations and to check whether the last 2 numbers are identical. So here we just compute the accuracy of LLMs correctly completing this test. So here is the result. We can see that all LLMs struggle in this test with accuracy lower than 10%, which is the level of random guessing. And we can also see that Llama family performs better than GPT, Huang, and DeepSeek models. They have higher accuracies than other models. Recall that in the first experiment, we find that Llama 3.1 can produce more realistic distribution on the number guessing game. So the 2 experiments together show that this kind of tests are related to LLM's internal working memory, and if they lack this human-like ability, they cannot perform well. So how about reasoning models? So this complicated math magic can be treated as a hard reasoning problem. So here we are using a COT on several long reasoning models, like adding COT to GPT-4o mini, GPT-4o llama, and also some long reasoning models like O-series model, QWQ, and DeepSeek R1. We can see that the performance has increased using COT, but the best performing model, which is DeepSeek R1, still has a accuracy lower than 40. So there is still a long way to go on this task. And another thing that is very interesting to notice, remember that in the first experiment, we find that all models have a preference over 7. So here, in the model's final response, we count how many cases are just models picking 7. So here, for DeepSeek R1, out of the 59 correct cases, it picks 7 for more than 80% of times. And this thing is also true for OpenAI O1 mini. So for the 25 correct cases, it picked 7 for 22 times. So here, maybe the models are maybe the models do not fully understand this task. Instead, they are just picking their favorite numbers. So the conclusion for the third task, the math magic, is this kind of task require LLMs to have internal imagination over a number, or say a object, and do some mental manipulation. This task is hard to improve even for advanced prompting strategies like COT. And the reason here is that there is no working memories for LLMs to do these operations. Do you have any questions about this experiment?
So I guess I have a question relating to the choice of the Josephus problem in general. And like this is the kind of problem that you see in your algorithms class. Like it's not something that the average human can compute in their working memory, like off the top of their head, especially if they're not familiar with the problem. And so I'm like, what if we're aiming for a human like LLM, but we also want it to be better than humans in some ways? Like, what would you consider to be sufficient performance on this problem for an LLM? Like, would you want it to be accurate all the time, or do you think that's like too high of an expectation because humans can't really do it very well?
Yes, I think for human, we have a working memory process information. I mean, to do mental manipulation on numbers, and we can easily complete this task and have two identical numbers at the end. So here, I think LLMs should have accuracy very close to 100 to be sufficiently human-like in this kind of task.
Okay, so follow-up question. What is the like distribution of correct answers like due to the, I guess, the properties of the problem? Is 7 a very common answer? Is just guess 7 like does that provide above random performance?
In our test cases, the correct answers are evenly distributed. But in LLM's responses, we can observe a particular preference on 7. I think this is because LLM's preference instead of like our predefined distributions.
Okay, that makes sense. Thank you. Are there any other questions?
Okay, if there is no other question, so let's just go through some existing efforts on evaluating LLM's working memories. Here, a very famous task is called the N-bad tasks. Human participants will receive a sequence of stimuli, and their task is to indicate when the current stimulus matches the one from N steps earlier in that sequence. For example, a text-based example will be here. We have a sequence of character, and they will present one after one to humans. And if we are performing a 3-bad task, the output will be here in this C and this C and this L, because 3 steps earlier, it was a C. 3 steps earlier, C, and also 3 steps earlier, it was a L. And we also have a visual version of N-bad task. That is, we can have some squares in different positions, and these cards are presented to human participants one by one, and the human participants will need to remember the positions and indicate when the current position matches the positions from n steps earlier. So when testing humans, an important thing to know is that human participants see the images one after one. That is, every time human will see only one image, so they need to put all the previous information in their working memory to perform this task. However, things are different in testing LLMs. In all the existing studies, researchers feed the whole sequence into LLMs. That is, for example, we will feed all the characters to LLMs and ask what positions satisfy the requirement of embed tasks. And in this setting, we can note that all information needed to answer the question is in the context of LLMs. So this is not the case when we test real-world humans. So evaluating LLM's ability using these embed tasks is just counting embed stimulus like n steps earlier. So this is a similar task with counting R's in strawberry. The reason is that we cannot hide the previous images to LLMs. So what we can do is feed all the sequence to LLMs. So here, the main challenge is that we need to design method to know what is actually in LLM's mind without knowing what exactly the object or say the number is in LLM's mind. So I think this is a biggest limitation on existing studies about probing whether LLMs have working memories. And we can always see that they have similar conclusions in with my presentation, that current LLMs lack sufficient working memory. However, I think this kind of evaluation method is just like counting R's in strawberries. We can also see that LLMs perform badly in such tasks. That's because it is hard for LLMs to do counting. Instead of LLMs do not have working memory. So here, I think to test whether LLMs can internally imagine a object or imagine a number, we cannot let the number or the object be in the context of LLMs. Otherwise, LLMs can easily attend to the information and answer the question. So the conclusion of today's presentation is we show that LLMs do not possess human-like working memories through the three simple experiments. Without this working memory, LLMs will show first unrealistic distribution or say unrealistic responses. Second, the LLMs will have self-contradiction. And finally, the tasks that require mental manipulation are hard to do for current LLMs. And you can find the paper in the following GitHub link, because arXiv is just it is holding my paper submission, and I plan to have a arXiv version before the presentation, but it's still on hold, sadly. So this is the end of my presentation today. Do you have any other questions?
Yeah, so are there any other questions, like either in the room or Zoom people? You're welcome to unmute or ask. John says thank you, but gotta go. So anybody either on Zoom or in the room have further questions for Jay?
Yeah, I guess I like that you've kind of identified some tasks that current models are bad at, and like the counting task, for example. What do you think are the solutions? I guess what can we do to train our models to do this? I know there's, I just looked up some techniques, like there's scratchpad, there's chain of thought prompting is also counted as a way to solve this because the models can read their generations and be consistent with their previous answers. But I'm wondering what to you seems like the most promising approach, and where should we go from here having these issues?
Yeah, thank you for this question. I think there are several ways to improve LLM's performance on this task requiring working memory. The first one will like a small RAG module with each LLM, that LLMs can write down some key information in a small module, and they can retrieve the information required for each task. And I think the current long reasoning model do a good job on this because they have the internal thought process that models humans' internal thoughts. So it is very related to our working memories. But there is but why we see current O1-like models perform badly in this regard is because the internal thought between several conversations are not continuous. So like when we ask LM at the beginning something, it will think a file and or say they will write something down in the internal thought. However, if we continue asking more questions, we cannot see the internal thought before, so they are not continuous. So this is probably a limitation for this O1-like models. And another way to solve this problem, I think, will be using some certain hidden states. That is, we can train LLMs with a specially designed hidden state to store working memory regarding the context. So this hidden state can affect how LLM sample their future responses.
Yeah, are there any other questions either in chat or in the room? Okay, then I think we can thank Jay so much for his talk. Thank you for being here, and I really enjoyed this. And thank you all for attending NL seminar this year. Thank you all.
Thank you.